Hi, everyone. Thanks once again for having me here. And this is really a joy for me to speak again at PosaDev. I think last year I was giving a talk and I really enjoyed it. It was fantastic. And also being able to talk about mathematics, because I know there's a lot of varieties of different talks here. And when I saw there was a call for papers, I thought, no, I have to talk about mathematics again, because that's an area which is usually not so much emphasized. And yeah, I'm really grateful to be here. And also thanks a lot to the sponsors of PosaDev, the wonderful organization, the recording of the talks, which I think makes it very useful for anyone who wants to see these talks later on, so that they are recorded. So I work as an independent consultant. I work currently for a company called Galva in the US. So they're specializing in trustworthy and safety and security critical computing, looking both at hardware and software and the whole spectrum. So this is a very important area when you have systems where you need to know that they work and they cannot fail, where you think just doing some ad hoc testing or even non-ad hoc testing is sometimes not enough. Before that, I worked in academia. So my specialty is in formal methods and verification. It's not so important to know what that means in detail, but it's an area which is very mathematical, and we're using mathematics to improve confidence that we can have in software. And part of this, I'm going to show you later, uses automatic theorem proving. So this is an opportunity, I would say, to learn a bit more what automatic theorem proving entails, why it is important, and how it relates to recent, I would say, progresses that have been made in this area, because we are living in a very glorious time right now with progresses in AI, and that also includes progress that we can make potentially in this area. I work also in semantic foundations, which is about the meaning of things and the meaning of theories, and yeah, so on. I've done both industry, academia a bit, and let's go to the next slide. That's not so important. So mathematics. So I have two slides here, one about math, one about computer science. So let's understand a bit better the difference. So mathematics is a classical field of, let's say, intellectual study and science. It's evolved over a long time. It hasn't just been created out of, thin air. It was initially largely driven by practical needs, kind of predicting the movements of celestial bodies, doing calculations of lengths and things like that. And it's very difficult to give a universal definition. So I was trying to do that here, but I mean, you can talk about, of course, numbers and quantities, but at some level, mathematics is much more about patterns and structures and shapes. And then we have areas such as topology and logic, which deal in a particular kind of structure, so I would say, and spaces. And it's also the relationship between all of these constants. And one thing you can say about math is that it provides a foundation for nearly all engineering and natural sciences. So we cannot do without it. It's inevitable. Here's a few quotes that I like. They're not always by famous people, but I think they're very nice quotes. So there's Carl Friedrich Gauss, and there's a few Germans here, so apologies for that. And he says mathematics is the queen of sciences. It's a very nice way of saying that the music of reason, and it's kind of the notes of reasoning in some way. Also, I find this a very nice quote, or the poetry of the universe, describing mathematics not just as an informal, but as a beautiful thing. It's poetry when you try to understand how things fit together. This is a bit more funny, sort of it's non-trivial and interesting things. So it's about things you don't expect coming out of simple things. And I saw a talk from, I think, Eduardo early on when he talked about the logistic equation. You have chaos emerging out of very simple equations and very simple problems becoming very difficult. So that is also that we get this non-trivial behaviors very easily. It is a game. Now, this goes back to Hilbert, who is one of the founders of this formalist school of mathematics, where you don't think anymore what it means. You just think about the rules of the game. And the point is that when you apply the rules, it doesn't matter what it means. You don't care about it, because you don't need any insight to know if something is correct or not. And you can just apply that without actually looking at the details of the symbols that you're actually using, they're interchangeable. I mean, some alien race could come to Earth tomorrow. They don't have the same number system. They don't have the same rules, but there will be some isomorphic connections between things, nonetheless, if they have developed mathematics. And it's a supreme judge that you cannot appeal to. And that is the really interesting thing also about math. There is no hand waving. Once you do a proof, that's it. And it will tell you, basically, the theories of math, if it's correct or not. And that's a very important thing that we need sometimes to know, to have this kind of supreme judge. It can be a little bit difficult, a little bit sort of annoying, but that is just the hard way we need to go through. And of course, you can create a belief out of mathematics that things are sensible in an intelligible world. So I sometimes find it comforting to have a mathematical law or theory that tells me something which I know is true, because it's very difficult to find truth, generally. So let's go to the next slide. Computer science is a fairly recent subject. I would say, I mean, it began probably earlier, but the discipline was maybe established in the 1950s. First thing that really deserved the name computer, well, other things deserve the name on computer. So here's a mechanism which dates back to 200 BC to predict movements of celestial bodies, and that could be considered as the first computer with a wider definition. But I think kind of generally we think Charles Babbage's analytical engine could be the first real computer that can do can execute programs. It's program controlled. Digital computers is the ENIAC in 1975. And these two, maybe you can think them as the fathers of computer science, especially Alan Turing with his ideas and his understanding of computation, or with his help for us to know what computation really means. Turing machines is probably something everybody heard about once. And nowadays the boundaries are very not so easy defined. I mean, computer science is invading everything, every field. So we have computers, we cannot anymore say very easily what's computer science and what's not. I have an opinion, but that might not be someone else's opinion. So there's a wide range. So there's some similarities. Both computer science and math are grounded in formal logics, and they're based, they rely on rigorous logical reasoning. And that's what I want to show you on the remainder of the slides. They have both their own languages. So in mathematics, you have a set of symbols that we commonly agreed upon and that we understand, like the symbol pi, I guess, is quite well known, but also other symbols in certain areas of mathematics, like the sum symbol, for instance. In programming, we have programming languages, which equally is a different kind of language we need to understand. And both of these have syntax and intuition and semantics behind them. So we cannot write a program without having a vague notion what the statements mean. But once we understood it, you can probably go from Python to Java to Kotlin, whichever, and you can still apply the same intuition behind these things. And it's a bit similar in mathematics. There's also fine differences, but there's a general understanding what things mean. They both rely on structure, problem-solving techniques, and abstraction is a very key element of both. So for example, in mathematics, we have group theory. And way before group theory was invented, we already could solve equations. We knew how to solve equations. But abstraction was the key to apply group theory to a lot of other areas, such as solving the Rubik's Cube, for instance, but also more serious things. So it's a very important subject. And programming, in some ways, also abstracts. I mean, we don't always want to care about hardware details or OSs. I mean, sometimes we do have to do this, but in an ideal world, we don't actually have to do that. Don't want to do it. So what's the relationship between the two? Mathematics provided foundations and theories to computer science. So computer science profits from mathematics through the ability to formalize, to specify precisely what we are doing. At the same time, mathematics can profit from computer science because it aids discovery and mechanization of proof. And why this is important, I'm going to show a bit later. But in short, it helps us to write safe and secure and trustworthy hardware and software system. Without mathematics, this would be impossible. So we need mathematics if we want or not. But also what we need is a toolbox. I mean, we cannot do everything on a piece of paper. Any non-trivial system, you would be completely lost with that. And these toolboxes exist, and there's a lot of them actually, way too many, in fact, in some ways. So I'm going to show you a few more of the tools that we have available. But it's very important that we have these tools. So just talking about tools, here's a list of them. And maybe you've heard of some of these tools. I mean, this one is a recent Microsoft, well, fairly recent comparing to the other Microsoft project to build a functional language with very strong formal foundations and verification support, similar to something like ML. I'm not talking about machine learning, but the actual functional language ML. So there's something called standard ML, which is a classical functional language. These are all theorem provers, and I'm going to show a bit more about this one, Isabel, just to give you a flavor. I don't want to turn you into theorem provers. It would be nice to do that, but it's a very deep hole that you can fall into. And there's actually, I have people who are addicted, seen people addicted to this in terms of once you get into it, sometimes it can be also a bit addictive, I would say. There's also other things which are a bit more traditional, used by Haskell programmers. I say a bit more about these. But most of the time, you would only find that people who are doing, let's say, specialized MSCs or PhDs in computer science are familiar with these. So this is also an opportunity to maybe spend 5 or 10 minutes to learn about this, because there's a lot of material available nowadays on YouTube and courses, online courses. So I want to give you a bit of taste how mechanized mathematics works. So what we're talking about here is taking a mathematical theory and using a program to make that theory analyzable and make it analyzable in a very precise manner. So when I told you that mathematics is a supreme judge, we also need to have someone who's the executive, who takes the orders of that supreme judge and carries them out. And that is kind of what these tools do for us. All of these, this one, this one, this one, this one, and this one as well. Say a bit more about that one. It's called COG. It's another proof system which is very popular nowadays with software engineers. So how does it look like? Well, you have an IDE, and on the right side, you're writing something which looks like program code, but actually isn't, but is a mathematical description. And if you're a functional programmer, you will actually see that some of these things, they will be familiar to you. For instance, data types. Most languages now have data types. I mean, Scala has enumerations, C has enumerations, which are vaguely corresponding to these. Then you have also data classes in Kotlin and things like this. So you find many languages support this in some form or another. You have definitions, which are here functions. You have functions, which you would usually find in functional languages and so on. So you can write your mathematical theory here, and then you can do things with this. And for instance, here I'm trying to prove something. You don't see that here because I haven't got the cursor in the right position. But wherever your cursor is, you kind of see something happening there. And you can verify some properties of your theory, some things you believe that are true or false. And here's a little bit just to make it quick to navigate across things. So you have different kinds of things here. You have data types, you have definitions, which could be functions or just constants. You have lemmas, which are properties that you want to prove. And it's pretty much like programming. So in some ways, you get immediate feedback, and you can see if your proof works. And if it doesn't work, you need to make up your mind if it does. Now, this example that I'm discussing here is a famous puzzle, is this river crossing puzzle. And if I just go back a slide, I don't know if I have it here, probably have it on another slide. No, it's not included. Yeah, here. We have a goat, a wolf, and a cabbage. They're on one side of the river, and we want to take them to the other side. So we need to do that in a safe way, so that the goat is not going to eat the cabbage, and the wolf is not going to feed on the goat. And it's a very famous problem. There's a small twist to it. What we're going to do is to mechanize this now in a language. Now, I'm playing games here. But in reality, these techniques are used similar for software. I mean, think of the problems of algorithms, where you have different things that you can do in an algorithm. You have different ways you can explore something, different constraints. And almost everything in this puzzle applies in that domain as well. But this is a bit easier to think about, I think, than just looking at an algorithm. So here is how it works. So we have all the three on one side, and we have a farmer in a boat who wants to take all of these to the other side. So let's see how we're going to do that. So that's our initial configuration, and that's what we want as a final configuration. So we can just start taking the goat. Just play around a bit. Take the goat. So I'm just pressing the wrong button here. So I need to explain a bit more because I got on this. So some constraints of this problem is that we can only take one item at a time. The other constraint is, I said, we cannot leave these two alone. And the third constraint is that we cannot leave these two alone. So I said this already. It's just I had this on the slide, and I didn't explain that. So how do we bring the items over? So let's try take the goat to the other side. What else we can do? Well, not much, so we have to go back. Are we in a safe state? Yes, because the wolf and the cabbage, they are not going to conflict. The wolf is not vegetarian, unfortunately. Fortunately, actually. And he's not going to eat the cabbage. So we're in a safe state, so it's good, we're going to go back. So what we're going to do now? Well, we could do something else. We can choose another item. So we can take the wolf to the other side. Now we have both the goat and the wolf on one side. And now is where the twist comes in. So if we just go back to the other side, we leave these two alone, then the wolf is going to feed on the goat. So the twist here is that we need to take the goat back to the other side. And now we're in a safe state. So we're not in a safe state if you just move the farmer back without nothing and just take the cabbage. So the twist is then we take the goat back. Now we have the wolf here. We still have the goat and the cabbage. And we're going to take the cabbage now, put it to the other side. Now again, we're in a safe state because these two, they don't, the wolf is not going to eat the cabbage. So we're going to go back and we're going to take the goat, it's the last thing we have, and put it here. And now we basically solve the puzzle. And the sequence of moves that we have is a solution to this puzzle. So how do we mechanize it in a theorem-proving system? So we use a stepwise approach. We define the objects of interest. We define the state space of the puzzle in a mathematical sense. We define the constraints of the puzzle. And then we define the notion of what a valid move is. And that is almost enough. I mean, with all of this, you can perform some analysis and prove, actually, that this problem has a solution, and we can even find the solution in a proof tool. So what are the objects? We have the farmer, we have the wolf, the goat, and the cabbage, and we can define this as a data type. So those of you who are Haskell programmers, they would actually see that this is familiar in some ways. I mean, if you do SML, you can almost immediately write the same thing in SML. And most other programming languages also allow you to write that. But it's a formal mathematical description. So this is how we write it in Isabelle. And everything I'm going to write now is what I showed you already in the Isabelle IDE. So we have the wolf, the goat, the objects, they have type object. And we can prove something if you have such a definition. You can already prove something about these things, namely that they're distinct. They're not the same. And there's no other object, no other value of this type. So these are two things which are basic assumptions that you make about type definitions. So this is a type definition. In fact, it's a data type definition. Next thing, we define the state space of the puzzle. So we have a few objects on the left side and on the right side. So here's the farmer, the goat on the right side, and the wolf and the cabbage. So how do we represent this? And this is where the mathematics comes in. So the mathematics says what we have here really is a set. It's not just a single element, it's a set of things. And the set includes two elements here. You have another set that includes two elements. And mathematically, the type of a set is P of some object. P stands for power set. Power set means it's all the possible subsets that you can have here because our state space considers all the possibilities of some objects, some of these 4 objects being on the side. So if we move to the mathematical world, this is how a mathematician would write this. And now we can write the same thing within a proof tool. So if I go further, we can encode this within our proof system. So Isabel gives us the possibility to basically say, here's an initial state that we start with, all the objects in one state, and here's a final state, and the puzzle state is exactly what I had on the previous slide, which is this cross product here of 2 things, one on the left, one on the right, being a power set. And if you know about the mathematical sort of modeling a bit, you would see exactly why it has to be like that. So we have our initial state, and we have a final state, and in sets you're usually writing this curly bracket notation. So these are all the elements which are inside the set on the left side. All the elements in the final state are on the right side. We also have like a void state, which is just the technicality. If you're reaching a dead end inside our search, we want to have that state. So let's go further. So we want to define the constraints of the puzzle. And this is very important when you do mathematical modeling, because it's all about constraints. When you define requirements as a software engineer, you're thinking often about constraints and properties of a system, safe states, things that you don't want to leave or that you need to ensure are kind of maintained. Last PosaDev I was talking about invariants, and this is also a type of constraint, an invariant. In this case, we want to have an invariant that the wolf and the goat must not be left alone on the same side. We want to have another invariant that the goat and the cabbage must not be on the same side either. So if we have a state of elements on the left side, so this is a set again, if you remember, and elements on the right side, so these are 2 sets, it's a tuple of sets. What are the formal constraints these have to satisfy? Well, if the farmer is not in it, so if the farmer says not a problem, we don't leave them alone because the farmer can overlook them. We don't want the wolf and the goat not to be a subset of L, and neither do we want the goat and the cabbage not to be a subset of L. Now, all of this natural language, hand-wavy thing here is now just one line of mathematical description. And this tells you how powerful mathematics is, because you can write all of this in one implication. So if the farmer is on the left, is not on the side, we need to have this constraint to hold. If the farmer is on the left side, the whole thing will be vacuously true. We don't have to prove anything. So we can go further and encode this in a theorem prover. So the mathematician would start here, and then once he realized this is what has to be true, he uses the language of the theorem prover. And the prover allows us almost immediately to write this. We have slight notational differences, like this implication arrow now becomes a single arrow, and also we don't have this symbol here. I think it might even exist, but I haven't used it here. And this is a definition of a function. This is a program. It's something you can execute. So I can basically translate this into code and execute it. And that makes it very interesting from a computer scientist perspective, because what you're writing is not just a logical formalism. Often what you want to write is something executable. And most of the techniques that we're using for verification are built upon concepts which are fundamentally executable. So hence, we can use this definition now to define what we mean by a safe state. So the items, this is a function which takes a set of objects, and it's this argument, and it imposes these constraints on those objects. And we want this function to be applied to the left side and the right side. And then we are in a safe state. And I can now formalize this in a simple definition to say, if that holds, I'm in a safe state. That defines the constraints of my puzzle. So the last thing we need to do is define the possible moves. And again, I'm defining a data type here, which only has one constructor, only one way to create values, which is a take constructor. And this constructor is a bit different. It takes a value of an object, which could be a goat, could be the farmer. And this is, in the end, what will allow me to express a solution to this problem. So we have only a single constructor. The constructor is parameterized by object. How do we encode the farmer going alone? Well, we could just say take the farmer. So the farmer is going to take himself. So this is enough even to encode the fact that the farmer goes alone. We just, as an object, the farmer is an object, we just put it here. We could have another constructor here for the farmer going alone, but we actually don't need to do that. So go alone is an abbreviation just for the farmer to take himself. So the last thing, and now it gets more complicated, I'm sorry this is as complicated as it gets, is to define what we mean by a move. So a move is basically a transition from puzzle state to puzzle state. And we can take an object, and we have also the state of our puzzle, which is the objects on the left and the right. And this whole thing just defines how the state changes. So for instance, if the farmer's on the left and the object that I'm going to take is on the left, then I'm just removing the farmer and the object from the left, hence the minus, and add it to the right, hence the union. And again, this is mathematics. But once you get into the weeds of set theory, and you know a bit in more detail what these expressions mean, it becomes immediately obvious to you why this is a minus, why this is a union. So you're taking something away from the left and you're adding it to the right. And you need to have two cases, either the farmer being on the left, because then he goes to the right, or the farmer being on the right, then he goes to the left. And you might also have the situation where the farmer, the object that you're moving, is not on the side that you're indicating in this take. And then you get into this void states. You're trying to do something illegal. So this is basically how we can have this action in just one definition, which is again a function that can be executed potentially. And you can impose a further constraint that then says, if we are moving to a state here, which is not safe, then again I want to be in a void state. This is a little bit where the experience in modeling comes in. So the more you know about this modeling technique, the more it becomes clear. But you almost always find that if you need to reason about programming, you need to look at abstractions. The code is all the forest sometimes that you're seeing when you don't see the problem. And this really breaks it down to the most essential parts of this puzzle. Of course, it takes a bit of time to write this, takes a bit of time to think that it's correct. You need to understand the notation, but it's not so bad. You have ifs, you know? That's something you have in programming as well, so that makes it a bit easier. So with this now, we can reap the benefits. How do I do that? Now, within the proof tool, I'm basically using a trick. I'm saying that there does not exist a sequence of moves that solves my puzzle. So let's digest this. Exists, this is a symbol for existence. I'm introducing a sequence of moves and executing these moves from the initial state, and we have already defined what it means to execute the moves through these functions. Those that might object, I would say, you have to fold this. So if you're a Haskell programmer, folding will mean something. You apply it again and again. So you can chain this, and then by folding, you can apply a move again and again. So you can apply this exec move functions to a sequence of elements, and you want to go to final state. So here I'm conjecturing such things does not exist. And there are tools to create something called a counterexample. A counterexample is something that proves, or that verifies that what you're trying to prove is bollocks. It doesn't hold. So it falsifies basically what you're trying to prove. So here, the trick I'm using is to say, well, let's assume this puzzle is not solvable. And let's use this quick check tool. And what happens now is quick check found a counterexample and takes me a solution, tells me a solution of the problem. And based on that, I can now take the solution, actually validate that it's a valid solution of the problem. So I can basically have a lemma that says if I execute the solution from the initial state, I end up in the final state. And I would expect this to be true if that is a solution of the puzzle. And what you can see is we don't need to be mathematicians to do the proof. There's a lot of tactics and utilities you can use to actually do this proof for you almost entirely automatically. And because all the functions we have can be evaluated and called, the proof tool basically uses all these functions and evaluates them for you. And then in the end, it's just an automatic step to say that this is a valid solution. Well, I wanted to do a live demo, but I might be a bit short of time and there might be questions, so I'm not gonna do that right now. But I will make the source code available if someone wants to play around with this. So the summary is we have taken a puzzle and we've given precise mathematical meaning to it, and we have done even more. We have put it into this Isabelle Hall theorem prover and used it to verify and find a solution. And this is how close you get to the truth, philosophically speaking. Mathematics is already the truth, but now we have truth that has been checked by a tool for us. So we know 100% that this is actually correct. The same techniques, as I said, I used sometimes to analyze safety critical software, like aircraft, medical devices, robots. And we're always trying to build models of things. For instance, what's a model of a pacemaker? We need to know something about medical engineering, of course. We need to know something about medicine in general, how the body reacts. But in the end, it comes down to playing these kind of games and to say, well, these are my parameters, these are my constraints, this is what can happen inside the system. Now, prove for me the system is not going to go into an unsafe state. Prove it reacts in the way that it should react. And this is where all of these applies. And tools like Isabelle help us. This is not always the only option. I can say something more about this, but it's a highly specialized process. And I think you probably agree with that. It's not something you do in an afternoon. But if you're interested in that, don't wait for permission to learn it. It can be learned, and it's not all of it rocket science, some of it is, but I think you always come out of this changing the way you think about software and changing the way you think about your subject. So, well, that wasn't easy. So here's a legitimate question. Do you expect software engineers to know all of this stuff? And the answer is no. What we usually want to do in formal software engineering and rigorous software engineering is to try to hide the semantic modeling and also the proof activities from the user. So you already have seen previously when I did this proof that all I did was say this apply auto. So I didn't have to do the proof. The proof was already done by the tool supports. And these tools are becoming very, very clever now to do proofs. They can draw from a large number of lemmas and theorems and knowledge. So they can do the proofs. And depending how I write my specification, they can do this quite efficiently. So most of the actual formal verification happens behind the scene, but we still need to know enough to write models in suitable languages. And Isabelle is a very low-level language. When you do programming, there are much higher-level languages which are based on what's called design by contract or contracting the design. They're sometimes based on model-based engineering, state machines, for instance. I guess everyone has seen a state machine diagram. Now, the cool thing is that this is not just slideware. If you do it in a tool which gives you the formal meaning of this, you can do analysis. You can check for deadlock freedom. You can check for live lock freedom. If it's a timed automata, you can do other things with it. So you are basically creating added value. So those of you who are more in the managerial side and in the architectural side, I mean, I really encourage you to look at what is possible with model-based engineering languages. And all the proof is done in the background. And there's actually a name for this, which is a secret ninja formal methods. So you think of the formal method as a secret ninja behind the scene. And there's, in the future, going to be much more automation in this direction. There is already a lot of automation, but we are moving really into these fields where we think software engineers, they don't want to know about proofs, they don't want to know about mathematics, so we need to make it easier for software engineers to use that. So some techniques is to use notations which are already closely aligned with what you know. Like programming-like notations, like the B method, for instance, has some notations that are already close to what you use in a program. And you're almost kind of tricked into writing a specification when you actually think you're writing a program. But there's, of course, a difference, because specification is precise, mathematically precise. Daphne is another language which tries to blend automated reasoning with programming idioms. So they're using something which looks very much like a program to write a proof. There are some tools that don't need any input. I mean, a good example is Rust, for instance, because Rust has a very strong type checker. And type checking is, in some ways, a mathematically founded technique. Well, not in some ways, it is a mathematically founded technique to to do analysis of software. And Rust is very picky as well. So if you remember when I said mathematics is like this sort of agent that is extremely picky, like the Merker in the Master Singers of Nuremberg or something like that. It's really a good thing in some ways because it tells us when something might be wrong, something might be foul. These tools, for instance, don't require any specification. They will just find problems by themselves. And Peter Hearn has been working, I think, a few years with Facebook, or quite a few years with Facebook now, to use very cutting-edge techniques in separation logics and abstract interpretation to find flaws in their source code without testing, just by looking at the code. And he's using that to build models of the code automatically by just looking at the code and then telling you if something might be wrong. I mean, you might have false positives, but they're finding thousands of bugs a month using these techniques, applying this to large code bases. And I really recommend to reading some of the articles of this article. And lastly, AI and large language models in the future will most likely help us to apply formal methods because they can write models for us and can help us to understand also what these models mean. And we can use then the tools like Isabelle as oracles that help the AI to improve themselves, which creates some kind of feedback loop. So there's a few milestones. TLA Plus, which I showed on previous slide, is used by Amazon and Microsoft. Amazon quite heavily is understood, and also I think it has found some bugs in the Xbox, in some part of the Xbox implementation. These languages are a little bit sort of well, I wouldn't say outdated, but not the cutting, where the most activity is now, and Haskell programmers like them. Lean is a very modern proof system, which is built on a new version of type theory. It's called homotopy type theory, I think. And it's at the moment the sort of latest sort of cutting. Well, it's where a lot of activities are now in the moment. F star as well is something that's worth looking at coming out of Microsoft, which also is a verification system, fairly recent. Isabelle, I just showed you, has been used to verify a whole microkernel. So this is not an easy feat to do. And all the way down from security, high-level security properties to C code. Coq was used to verify a compiler, a whole compiler. Everything from parsing, syntax, all the way down to code generation, optimization. And this actually got an award because of just the scale of what they achieved in this project. All of this done in a theorem prover. And there's a lot of other languages that can be mechanized. For instance, WebAssembly recently, I think, has also been mechanized. And I couldn't list all of this because there's just so much happening. So what is the other perspective? So we think about, we've seen now how mathematics helps computer science, but I promised that this is not just the one-way connection, but also that computer science helps mathematics. This is a famous proof that has been automated quite some time ago, I think even in the 80s, where they want to prove that every map can be colored with 4 colors without 2 colors clash, or two of these surfaces having the same color. And this was proved automatically to some extent by computers because you can reduce this proof to a given number of configurations. And it was just beyond, let's say, the human sort of, well, you could have probably done it manually, but you need a lot of people to do that. And it was basically through automated proof kind of solved. The proof has been improved over time. I think they can reduce the number of cases. And I mean, the original, there's a book, I think, about this, which has about 400 pages of microfiche that probably enumerate some of these cases. But this is a classical example where you use mechanical proof. If you have something which has a lot of cases, which are maybe not even that difficult to solve, but having someone sitting there doing that will be tricky. Terence Tao, I'm not sure if you heard of Terence Tao. He's probably one of the stars, one of the sort of celebrities, top 10 celebrities, probably top 5 celebrities in the world of mathematics. So he's done a lot of fundamental work. He made progress on the Collard's conjecture, which is one of the most difficult problems, even though it's very simple to state it. And mathematicians are discouraged from looking at it because they're wasting whole careers just finding a solution, never getting anywhere. And there's something very interesting. This is a guy behind Lean, and Terence posted something that the combination, of having these tools available in modern AI techniques, GPT, helped him a lot to understand how to use these tools. And I think in the future, we'll probably make much more use, even in the area of mathematics and formalization, to use things like Copilot or other tools surrounding this that help us to write models, but also to understand what they mean, because these AI programs have become much better, and LLM models, to explain what they're actually doing. And if you give them the right prompting and tell them what you want them to do, they can also give you very good advice. So I didn't do this, but I wanted to develop this whole example just with GPT. So you treat the GPT maybe something like an eager student. And you tell them, no, you made a mistake there, can you change this and that? And eventually they come up with the right solution. And for a problem like this, this would probably not take you more than half an hour without probably knowing all the details. So this is a very kind of hopeful thing. So I'm kind of slowly getting to the end of the talk. I'm just going to take 2 more minutes. So a larger project of this mechanized mathematics is all of mathematics should in some way be formalized and mechanized in some theorem provers. There have been efforts in this, and you can look at these different efforts which already provide huge libraries in different flavors, I would say, that try to mechanize this large body of mathematics that we have. And it's constantly evolving. So we have in the future probably more and more of these things being done so that mathematicians can just use them when they want to verify some proof or, and it's always a problem in mathematics when you have a really cool idea to solve a really difficult problem. It takes years before that problem will actually be accepted to be proved because some of these proofs are quite intricate, but mechanization, you can trust it. And that might also short circuit some of these turnarounds. So I'll make the slides available, and this will all be on the slides. There's a particular challenge of formalizing 100 theorems by Frick Wittig, I think. I'm not sure it's spelled. And this also gives you an example where these provers are. So it's a bit like a high score list. Which prover has done the most? And this tells you also something about the communities behind these proof systems, how active they are. So in conclusion, computerized and mechanized mathematics is a really big topic. And I didn't want to scare you about this. I mean, it maybe looks a bit scary, but as I said, we are working very hard on making this more accessible, and it will become more accessible. In the same way, you might think of AI being something you need to learn about. I would say this is also something you should maybe take a bit of time to learn about. As a software engineer, we can harness this technology and power without getting too deep into the rabbit hole. And sometimes you can do that through high-level notations. And this will be a different talk, but you have high-level notations that basically hide some of like the low-level mathematical formalisms, and you don't have to use all of that. And many tools, like MBSE tools, exists that under the hood using formal methods. So FramaC is a tool for verifying sealed programs based on a language called ACSL. AtelierB is a tool where you can start from specification, you go all the way down the code by gradually refining and making your implementation more precise by adding details to that. You have the same thing as FramaC does for C, OpenJML does for Java. So basically you can write specifications of your functions and then use a prover to prove that your implementation is correct and doesn't crash, doesn't deadlock. And you have also tools which are more integrated with IDEs. So it's almost like you're writing code and then the IDE tells you, oh, you're doing something wrong there. Maybe you should think about this again. And yeah, TLA I mentioned already. This is also a very often used formalism for systems. So further reading, have a look at it. Software Foundations is quite a big work. It tells you how do you do things in Coq, how you write formal algorithms, verify algorithms in Coq, going through different kind of aspects. Lean, as I said, is at the moment very popular. There are some interactive tutorials. For those who program Haskell, I would recommend maybe this a bit more. This is a bit heavier going, but you might find a lot of similarities, and there's also some historical review. So thanks very much for listening, and I think this is very different from usual, and yeah, thank you if you have any questions.
Thank you. Thank you, Frank. I guess we have just time for one question. So does anyone have a question? Okay.
Because why not? So do you think that the large language models will help to produce more formal specifications? For example, it's kind of complex building it from scratch, from your mind, unless you have a well understanding of the specification language, that it's a mathematical language after all. So asking something like ChatGPT or whatever large language model application can produce kind of like a translation between plain English or Spanish or whatever to formal language. Do you think it's like the way to go?
Yeah, I think this is a very good way to go in terms of making these techniques more accessible. The large language model, they're very good dealing with prompting and language. The main issue of these things is always to tell precisely what you want to the system. And most of them faults are actually done when people don't really know what they want. And you need to force them to say exactly what you want. The other thing that large language models are good is to make a proposition. They can give you something and you can ask them about it. And they explain, look, this is an invariant, this is a definition. And this is also a way of learning in some ways, because it forces you to understand what the tool is telling you and change it. So I really think there's an opportunity also for large language models to, let's say, make it easier to write these models. And this happens, is not just for formal methods the case, it's also for all of computing the case now. I mean, we are probably the last generation that really knows how to program. I mean, I don't know what happens in 20 years and 50 years, but I don't know if any, there's a story from J.G. Ballard where it was outrageous to write poetry in some future century because computers are so good, so all you do is tweak the buttons. And someone writes poetry, it would be crazy. So who knows? I find this vision a bit scary and maybe also a bit sad, but that's the way. And if it opens opportunities for more, let's say, engineer to use these methods, I think it's all good.
So the actual, well, one of the problems will remain the same. People has no clue what they want. They have no clue what they are their requirements. So it doesn't matter that your requirements are like super specific because people doesn't know specifically what they want. So we need to be good software engineers to translate problems into.
Exactly, and I think for us, it will be not a niche, but more important that we're actually getting into this higher abstract way of looking at things and not getting too trapped into technologies. I usually start my talk with an overview of relationships of that, but I think if we want to make sure that we maintain our importance, that is where we need to look at, because all the coding maybe at some time will be more automated. Thanks, very nice question.
Thank you, Frank. Let's give him an applause, please. So yeah, thanks, Frank, once again. We have one activity here in the community room. Then we're going to have closure at Pamphilo. So yeah, so if you want, you can go to community and then to